Thank you, Meyer. I'm Randy Bass with Snobble Engineering. I'll be one of the principal instructors this morning. But I want to welcome you also. I've been involved with the Georgia Safe Dams program since its inception in 1978. So dam safety is important, as Myra said, and we are glad that a lot of the dam owners are here today. To mention, my name's Randy Bass. The other instructor is Joe Monroe from Snobble Engineering, also from the Atlanta office. If you need to contact us later with any follow-up questions, there's our phone numbers and email addresses. One thing you'll find later in your package of information, you'll be able to get a CD that has all the presentations on it. Those will be handed out later. So following this, you can go back to your own computer and go back through the presentation. If you have a question or a concern, please contact us. We'll be glad to answer it for you. Logistics. John, you're going to cover. John. But quickly, you have in your blue bag a lot of good information, pamphlets from ASCSO. There's also a form where you can write down a question. And what we're going to do to try to, for the sake of time, is during a particular presentation, don't ask a question, but at the end of the day, we'll take all those questions that you wrote down and answer them all at one time. So look in your bag, and as we go through the day, if you say, all right, I got this question, write it down. There'll be a drop box in the back. So during a break or a lunch, we'll put it in there, and we'll collect them and answer them at the end of the day. Restroom, I think if you go out, I remember I go out the back and kind of go to the left, there's restrooms. If you keep going around, that's where I think most of you found where there's coffee. That's where the break will be, and the lunch will be served also. Any emergency, one thing, if you have a cell phone, please put it on vibrate, turn it off, put it on vibrate if you would at this time. So these workshops would not really be possible if the Association of State Dam Safety Officials, which is ASDSO, wasn't involved. And also FEMA does a lot of funding for these state programs. So between FEMA and ASDSO, that's what makes these workshops possible at a low cost. I mentioned you got the handouts in your bag, so refer to those as we go through at the end of the day. But there's a lot of good information in your bag. A little bit about what ASDSO is. And it's really it's a nonprofit organization. It's developed by the state dam safety officials. And there are 49 states that have dam safety programs. Alabama is the only one that does not. ASDSO was established in 1984. But a little history, when I was with the Georgia program, Georgia, South Carolina, and North Carolina started what they call a tri-state dam safety conference. The very first one, I believe, was in 1980. After we had, and the first conference was actually in Greenville, South Carolina. For the next 2 years, the next one was in Atlanta, and the next one after that was in Raleigh. And then we decided, those 3 states, to say, why don't we make this a Southeast dam safety program? So we actually had a program in Orlando, Florida, for the southeastern states. But we invited all the states, and we said, all right, this thing is growing. We got to start looking at a national program. That's where it started in Orlando. We got most of the states came. We actually started a national dam safety program. And that was really the roots for the ASDSO as you see it today. So it's a premier organization. They have annual conferences. They have regional conferences every other year. For the Southeast, the next one is in Asheville, North Carolina next year. They do workshops, they do webinars. It's a very active program. And it's really also for, not only for us engineers, but for dam owners. They're going to start developing webinars, which are 2-hour webinars for dam owners to help you with how to inspect the dam, how to maintain the dam, and emergency action plans. So look forward to seeing that. But it's a very great organization. Join ASDSO. You as a dam owner can be a member. And it's less than $100 a year. I don't know the exact number. It's not expensive to be a member, but you'll get emails a lot about educational programs coming up. And you as a dam owner, it's almost free, so it's good information that, so if you're not a member, think you should consider joining them. Here's the website. Very good interactive website that it's easy to navigate through. So when you have free time, just look at it and look at all the opportunities and the publications and the training that they offer. Well, FEMA provides a lot of money, both for ASDSO, but also the state program. Almost every state program gets a grant, and it depends on how many dams they own, depending on the grant level. But it helps the state program hire people to put on programs like this. So FEMA works through what's called the National Dam Safety Program, in which they just actually renewed it in Congress in the last couple of months. So FEMA is a big player in dam safety. So this workshop, we're going to give you a lot of information. It's going to seem overwhelming at times. We're going to not get real technical, but there's a lot of information about parts of dams, how dam operates, how dams can fail, how you should inspect the dam, how you should maintain the dam. So there's going to be a lot of information. We're going to talk about liability. You as a dam owner, the dam where the fail and hurt somebody, you can rest assured what the attorneys are going to do. So you have a lot of responsibility and liability because you own the dam itself. And then public safety around dams. You know, obviously water is an attractive nuisance. And we're finding nowadays that particularly the overhead dams where you see canoes and all people actually go over the dam and they drown because they can't get out of the turbulence. So it's an attractive nuisance. So in terms of signage, gates, and locks, you the dam owner got to think of those things. If somebody gets hurt on your spillway or your dam, the lawyers are going to be knocking at your door. Dam failure modes. How do dams fail? Because what's important when you go out and look at your dam, when you're mowing the grass or cleaning debris out of the spillway, you see those dams every day you're out there. So we want you to be able to identify if there's a problem developing at your dam. You're going to be the first ones to see it. So throughout the day, we're going to give you pointers on what you should look for when you're actually mowing the grass or walking on the dam itself. Because dams can fail in a variety of ways. And a lot of times you don't see those until the dam is actually failed. But there are some that have some early signs that you should be aware of. Emergency action plans, very important. So if we have another hurricane come through South Carolina, drops a lot of rain, your spillway may be designed to be adequate, but if you get 30 inches of rain, most dam spillways will not pass those storms. So emergency action plan is when your dam is in distress, what you want to do is minimize loss of life downstream. So emergency action plans are developed for that very reason. If your dam develops a problem, even though it may be perfectly safe, you want to be able to at least evacuate the people downstream. And part of that, we'll cover later, is you developing a relationship with the emergency management officials so they know where your dam is at and you know who to call in case your dam is under distress. We're going to talk about typical repairs of dams and what goes into that, but also you're going to have to first hire an engineer. And we're going to walk through the steps because that's an expensive investment. And when you want to hire an engineer that's qualified and can meet your needs, but also understand the South Carolina Dam Safety Rules and Regulations. So we're going to walk through kind of a process, you as an owner, what steps you should take if and when you have to hire a professional engineer. The agenda today, this introduction will go through a lot about the definition of parts of the dam and things of this nature. The South Carolina Dam Safety officials will come up and talk about their rules and regulations. We'll have a morning break, which the coffee and the danishes are out in that room. The rest of the morning, we're going to talk about failure mode, how dams can fail, the different processes that create not only the dam, but the spillway, the parts of the dam. We'll have lunch provided. The next session after lunch will be operation and maintenance of dams. Then session 5 will be how an emergency action plan is developed. Section 6 is public safety, security, and liability. 7 is funding, I say funding, that's going to be a very short talk. There's not a lot of money out there to be given the dam on this. But we'll go through that. And like I said, how hard a typical walkthrough, say, example, here's this dam had a problem, here's how they fixed it. And then we'll do the wrap up, and that's where we're going to do the Q&A. Again, if you have any questions, write them down, we'll put them in the box at the back of the room, and we'll answer every one of them before we leave today. Local dam safety resources. Here in South Carolina, like I said, South Carolina's had a dam safety program for a long time. And because of the recent flood events, they staffed up, they changed some of the rules and regulations. But as Myra said, there's a partnership. Even though they are the regulators, don't look at them as the enemy. It's got to be a partnership because they have people in emergency that come out and if your dam's under distress and look at it and give you some assistance. So look at them as a partner and use it. They divide their state up into 6 regions. And each region has a regional office and has an engineer there in the region. So get to know these people. If you're in Region 1, you want to know Hannah. And I think we have all of them here, Jill.
They are all but one. So when they call your name, they're kind of spread out.
All right, so Hannah.
Hannah's actually
Right here is Region 1, Chuck in Region 2. We have Caitlin in Region 3.
Yep, Caitlin's not with us.
Ryan, Region 4, right here. Danny in Region 5. And 6, actually is vacant at the moment. Scott is still involved with the program. He's no longer in the region, so that is a vacant position at the current time. But this is their contact information. Like I said, it'll be on that CD, but get to know them. Again, that's your local resource in the region. And then you have the state office with Jill and John. Anybody 12-year-old or younger, we would have them come and visit this. Additional resources. The U.S. Department of Agriculture, the NRCS, it used to be the Soil Conservation Service. For all of you that have gray hair will probably remember the Soil Conservation Service. Back in the day, they had a lot of they would actually design and had pay for building a lot of farm ponds for irrigation and for cattle drinking. So a lot of the older dams all over the U.S., the Soil Conservation Service had a lot of hand in designing those little farm ponds. Now it's the Natural Resource Conservation Service. And in a lot of states, they have what's called the small watershed or flood control dams that they built. There's over 10,000 of them in the United States. And so, but they're a good resource. They have a lot of design aids because they were involved with a lot of dams. So your local water conservation districts, again, you can use them as a resource. They have a lot of information on how to repair a dam or how you should maintain a dam. So if you're a local water conservation district, get to know that person, so that can help you also. The bigger dams, you start talking about the Corps of Engineers, the Bureau of Reclamation, Federal Engineering Regulatory Commission. If you got the bigger dams and you want to get really down in the weeds technically, they've got a lot of publications on dams. So if you're just interested in the subject matter, you can download a lot of their information for free. And then local engineering consulting firm. There's a lot of them in the Southeast that work on dams, and they have a lot of history and a lot of information on dams also. So let's talk about dams. We'll start the program. We're going to talk about the functions of dams, dam types, the terminology we engineers like to use when we're describing dams, and there's all sorts of types of spillways. So let's quickly go about the function of dams. And really, a dam will do a lot of these functions. One dam may do 4 of these. So flood control, a lot of these NRCS flood control dams are strictly for flood control. Water supply, a lot of municipalities obviously have reservoirs for that. Hydropower, South Carolina electric and gas. Waste impoundments, wastewater impoundments. You'll see a lot of water treatment plants. These will be generally small dams. use that for sediment, dropping out the sediments in the lake before they treat the water. Irrigation for farmers use, navigation along the rivers, the lock and dams, and then almost every lake has a recreational component. The flood control, this is a typical NRCS dam, and a lot of times they'll have a reservoir out in the lake, but a lot of times there'll be a large distance in elevation from the lake level to the top of the dam. That's the flood storage. So if you have a big storm, the lake goes up, slowly drains back down. Water supply can be any type of dam, but there's a lot of them in South Carolina, obviously. If you're going to have these water supply departments, you can't just pump from a river or a stream all the time because you may be in a drought. So they'll build a reservoir so when there's a drought, there's a pool of water they can draw from to treat. Hydropower, waste impoundment, a lot of clay mines, gold mines, they have to have a place when they're sluicing and cleaning up to get the minerals. They have to pump that water behind the dam to let it settle out before the water goes to the stream. Here's one that the kaolin industry uses a lot of dams. Wastewater storage, usually these are not large dams or large lakes, but there's a lot of them out there. Now the irrigation, particularly out west, and then the lock and dams along the rivers themselves. So here's actually, like in this case, the dam and the spillway, they're all, a lot of times they're one and the same, and then here's the lock chamber itself. And then, like I said, almost every component is recreation. Quickly, type of dams. Over 90% of the dams in the U.S. are earth-filled dams. So the vast majority, generally it's cheaper to build a dam out of earth if you have it. You can have rock fill where most of the dam, it looks like a pile of rock, but in the center there is an earth component to keep the water from flowing through. Concrete gravity dams are old masonry dams. A lot of the old mills in the southeast that are masonry dams built out of rock. Gravity dam is just like the word. They're built out of mostly concrete and they're there with weight. The gravity what holds it down and keeps it from to tip over. You can have arch dams. You see some large ones, particularly in Europe. And an arch dam is designed because you don't have to use a lot of concrete, using the curvature of the dam to resist all the forces wanting to turn the dam over. So, but you got to have the right geologic formation to have an arch dam. And a buttress dam I'll show you. In the old days when labor was cheap, you see a lot of buttress dams. But now that labor is not cheap, you don't see really any new buttress dams being built. Then there's the oddball dams. You can find a steel dam, not many. What's called a rubber dam. A lot of times nowadays you'll see some fairly large dams, actually they're rubber bladders that hold back the water, and wood or timber crib. And those are generally your older dams also. Show you some examples. Earth and rock. Here's a rock fill. You see those are very steep. All you see is rock on both sides, but in the center there is a clay component, so that's got to prevent the water. You generally find rock fill dams where you don't have much clay soil to build. So if you're limited to how much clay soil is in the area, generally you may see a rock fill dam be built. Earthen dams are just like it is. It's earth, grass. It may be a zone embankment. It may be made up of a couple of different types of earth. But like I said, over 90% of them in the U.S. are earth dams. You might recognize this as Saluda Dam. The original dam, which is the green part, was what's called a puddle core dam. It's basically earth, but the center of the dam, the way they built it, was they pumped water into it, let the water settle out, and that would be your clayey fine material. The problem with that construction, you have an earthquake, that material that was pumped in there becomes liquid again and causes the dam to fail. So South Carolina Electric and Gas built what's referred to as a backup dam. Here's the gravity concrete section, and this outside part are rock fill. The reason they put a gravity section here is because there's a powerhouse here, and you had to make a lot narrower dam, otherwise the powerhouse would have to do it. It's built out of what we call roller compacted concrete. It shows it during construction. It's a concrete dam. It's just built a different way than the way we originally built concrete dams. It's referred to as a buttress dam. So you can tell it doesn't use as much concrete as a gravity dam. So back in the day when labor was cheap, you could do all this form work. But nowadays, because labor is not, you don't see many buttress dams being built anymore. And the problem with these, particularly in an earthquake zone, when the earthquake wants to move the dam left and right, a lot of these buttresses would collapse. So a lot of these, the way they fix those, they basically infill between each one of these buttresses with concrete made of gravity dams. So that was the repair method for these to make them resist large earthquake events. The only steel dam I'm aware of is actually made out of steel. You don't see, I don't know if you're going to find any in South Carolina. A rubber dam, you don't see the dam, but it's actually a big rubber bladder. They just put air in it. This is one in Arizona. And actually they replaced it. They changed it because you can imagine the heat, and you got the rubber, the UV light, that rubber deteriorated. They actually had one of these break, deflate, and drain their lake. So they ended up putting in steel gates just maybe 2 years ago. But you see a lot of smaller rubber dams, maybe 5, 6, or 7 foot high. These are like 30-foot high rubber dams, one of the biggest ones in the U.S. Timber crib, old dam. Even though here's they're restoring one with timber crib. Basically, it was timber crib and in between was rock. So you say, well, doesn't the dam leak? Hell yeah, it leaks. But the problem was, they're on such a large watershed, it can still leak, but still keep a reservoir. But you would have water just flowing through the rock, but there was enough resistance that it wouldn't drain the lake. So a lot of old ones are built this way, kind of run-of-the-river type structure. But you got to remember, regardless of the type, you got to inspect it, you got to maintain it. Each one of them has a little different little kinks of what things you got to look for. And we're going to mainly focus on our comments on earth-fill dams. But if you own a concrete dam, please, if we don't address your comment, ask a question at the end of the day. Let's talk about parts of the dam. I want to make sure when we use terminology as engineers, we're all talking the same language. All right, reservoir is an easy one. The principal spillway is the spillway that controls the normal pool of the lake. Generally, it's a riser structure out in the lake connected to a pipe that goes to the end of the dam. That's called the principal spillway. The upstream slope is the slope on the water side. The crest is the top of the dam. The groin referred to is where the dam meets the natural ground. And that's important because a lot of problems can occur where the dam meets the natural foundation. The outlet works is where the pipe comes through the base of the dam at the downstream slope of the dam. A toe drain, what we have prevents a dam from seeping, because keep in mind, all dams will leak. That's guaranteed. What you want to do when the water comes through the dam, you want to collect it. And so what we call a toe drain, we may call it a trench drain, we may call it a chimney drain. It's actually a drain made out of aggregates, generally sand and gravel, that's in the dam that collects that seepage before it comes out the back side, and it comes out of a pipe. And we'll show you examples of that. So most old dams don't have them, but any new dam will have some type of what we call internal drainage system. That's where you have a toe drain outflow. What's good about it is you want to be able to measure the flow of water coming out and get these drains, because that's an early indicator if you've got a problem. That should almost be fairly constant. But if you see it triples in the flow rate or it goes away, something's probably bad going on inside your dam. If muddy water is coming out, it should always be clear. It's almost like a spring. You almost can drain it because it's going through a sand filter. But if it becomes muddy, you've got a problem. So those are the type of things you look for when you're mowing your grass. You take a look at your toe drain. Now I got water coming out. I never had water before. Those are early indicators of the possible distress of the dam. Emergency spillway, or what's called an auxiliary spillway. If you have a big storm event, those are the spillways where the floods go through. Sometimes they're concrete, most of the time they're called what we call vegetated, they're grass-lined spillways. All right, well, I'm going to take a slice through a dam now. And this is a well-designed dam. So you have your riser, it goes through outlet pipe. This is what's called in this section a zoned embankment. It's actually made up of two different types of soil. What's called the core is your more clayey, impermeable soil. And then the shell material, the soil on both sides of it, it can be less impermeable. In this case, you have a vertical filter drain, it goes to a blanket drain, so any water wanting to come through this material gets in this drain and drains out. It keeps the back of the dam dry. That's the main purpose of these drains is if the back of your dam becomes saturated, it becomes unstable, and you can potentially have a slide and you lose the back of the dam. So these drains keep the back of the dam dry. Sometimes you'll have a berm or a dam will actually come down. There'll be a berm. On a tall dam, you generally have berms because otherwise rainwater, when it flows down a 60 to 80 foot zone, it's more inclined to erode your dam. So a lot of times you'll break that up with a berm and collect that water and run the water off to one of the groin areas. You're here in South Carolina on the coastal areas, there's a lot of sand. Obviously, water goes through it fairly quickly. If you have a dam, you got to have a cutoff to prevent water from running under the dam. So you have here's like a sheet pile wall, cutoff trench, somehow to make that water more difficult to go under the dam. One thing you want to do, the more you increase the path seepage has to follow, it decreases the velocity and increases the quantity. So you just want to increase that seepage path. Risers need to have a trash guard to prevent trash from clogging up your spillway. You'll see a lot of slides of this earlier. But if you have a storm, generally you're going to have a lot of trash washed into your lake, and that's going to be collected on your principal spillway riser, and it can clog it up. The next thing you know, your principal spillway is not working anymore. Upstream, downstream slopes we covered, the abutments, the groins. I'm going to show some pictures of each one of these, and also instrumentation. Probably most of your dams have no instrumentation. That's not uncommon. But a lot of dams now, you'll have a survey monument on top of the dam to see if it's settling or moving. You'll have piezometers that will measure the water pressure inside the dam to see where that seepage might be occurring. And if you do have enough seepage, you may have a weir that actually you can measure the flow rate by the water flowing over it, what's called a D-notch weir. Downstream slope, pretty obviously that's on the downstream side of the dam. Abutment and groin, as I mentioned, here's the dam, here's the natural ground, so this is the abutment and groin. Like I said, you can build a real good solid dam that will minimize seepage and be very safe. But what's also trying to occur with that reservoir is water's trying to go through the natural ground now too. And you don't know what that consists of. And so you got to be careful because sometimes your dam may be perfectly dry, but the next thing you know, you got water coming out of this side drain. And you can have a failure of the foundation of the dam, which can be, if the foundation fails, that will cause your dam to fail. So you got to not only look at your dam, you got to look at what we call the abutments to make sure you don't have water coming out of that. Spillways, you can have principal, let's say, and emergency spillways. This is a spillway that is the principal and emergency spillway, and it's all concrete. When the pipe comes out of the back of the dam, the water coming out of those pipes can be 30 or 40 feet per second. And it can really cause some erosion. So you have to have what we call a stilling basin or a plunge pool. So when that water comes out, it falls down, and that velocity of the water in this stream just slows down the creek. So you got to have generally riprap to protect the downstream. Mentioned trash guards to show you some examples. You want the leaves and everything to go through. You just don't want to start building up sticks and logs, and then those leaves will start matting over the spillway opening, and your principal spillway doesn't work. So you see all types of different trash guards, but you need a trash guard to prevent the sticks and the timber from getting down inside your pipe. But believe me, they're hard to get out of these. All of a sudden start going down into the right pipe. This is an example of an internal drain the way they should be built. If you got a seepage problem, generally this is a typical section of what happens. Here's the soil of your dam, and if you put gravel directly against the soil, over time that water is going to cause that soil to get inside the gravel and clog your drain. So your first line of defense to prevent that is sand. So you see the gravel itself is surrounded by sand, so the water from the dam will get in the sand, but it won't let the soil from the dam get into the gravel. And then in the gravel you have a perforated pipe, so the water gets in the gravel and drains out the pipe. So this is a typical well-designed internal drain for a dam. And then you have the outlets. And you see here's the right drain, the upstream drain, and this called the chimney drain. You label them so you know where the water is coming from. And you'll notice these metal things, those are called animal guards, because animals love to get in drains. So you have these guards that keep the muskrats and all that from climbing up in your drain and building a nest. That's important, because they love it, because they'll get up in your drain and clog your drain up. The riprap, if you got a big enough lake, you got to worry about wave action causing erosion of the upstream slope of the dam, and generally riprap is used to prevent the wave from eroding in front of the dam. If you got a small lake, just a grass slope is adequate. We use the term freeboard. That's the distance between the lake level and the top of the dam. As I mentioned, every dam acts as a flood control dam. It holds back some water. And I'll show you later what's important in terms of your spillway capacity. A lot of it is based on that distance from the lake to the top of the dam. A little bit about instrumentation. Monitoring wells, they're basically holes drilled in the dam. They got a perforated pipe, they got sand around it, and it just measures it'll show you where the water level is inside your dam. And it's important because when you measure those, again, that water level, unless you have a real long period of rain, that water level should really stay about constant. You measure if it's going up or down, something's going on inside your dam. It's generally not a good thing. Seepage weir, if you don't have like I showed you those drain pipes, a lot of times it's just a channel going into a V-notch weir, and you can measure that flow rate coming out of a V-notch weir. So there's different levels. Saluda Dam has a ton of instrumentation. Obviously, it's a large dam, so there's a lot of different, more complex instruments. But for probably 99% of you guys, you may eventually have a monitoring well. You may eventually have a seepage weir. Quickly on types of spillway, because there's different types and there's reasons for different types. You have conduit, which are pipes or culvert, open channel spillways, which just like it says, is an open channel. And then you have what's called weir spillways, and there's different types of weirs, and I'm going to go over some of those. This is the only math we're going to do today, so don't worry. This equation is important though. I want you to understand when you're talking to an engineer, the Q is the capacity. It's like cubic feet of water per second. The equation is how much will how much water will my spillway pass? Well, there's three variables. C is a coefficient. It depends on the shape of the top of the spillway. And I'll talk about some of those. That's important. That value can range from about 2.5, say, to 3.5. Simple. L is the length of the spillway. All right, if I got a spillway 100 foot wide, that's pretty simple. But nowadays, you've got different shapes of spillways to increase that length. And to increase that length in the same width of the channel. To show you an example, you see how this is a labyrinth spillway, so it's kind of like a zigzag. So your length is actually the length of each one of these, so you can get it very long. What's important is the H, because that's raised to 3/2 tower. So the H is the height of water over the spillway. So if you don't need a lot of spillway capacity, increasing the age is better than trying to change the C or the length. And this goes back to freeboard. If you've got, say, 5 feet from normal pool to top of the dam, that's what your age is. And a lot of people say, well, I need more spillway capacity. Well, the best way is to increase that age. Lower your lake, increases that age. Raising the dam, increases that age. So a lot of them, you talk to the engineers, they're going to come to you and say, all right, can you live with your lake being lower 2 feet? If we do that, that H number goes up. Or is there a practical way to increase the height of the dam a little bit? And again, that gives you that H. So those are things, when an engineer is talking to you, you got to make a lot of decisions, long-term decisions. But that's the equation that tells you my capacity to spill. A little bit about conduit spillways. Usually it's a vertical riser pipe connected to a horizontal outlet pipe. The old days, those pipes were made out of corrugated metal. And those have a design life anywhere from 20 to 40 years. And eventually they rust out. Here's again, a trash car. You should have a trash car. Here's a square one, reinforced concrete with trash cars. These outlet pipe. This is a ductile iron pipe, and it has a plunge cord made out of rubber. You gotta have it. Show you kind of a cross section. Here's the inlet, the pipe. In the old days, we used to put what's called anti-seep collar because any penetration through a dam is a weak point. That's where the water is going to flow around along that pipe. So, to prevent it or minimize it, in the old days we put these collars to make that water, when water is running along that pipe, outside of that pipe, it has to go around these collars, increasing that seepage path. You increase the seepage path, it slows the water down and prevents it from generally causing a big problem. But we found over the years that those are difficult to construct. And if you don't compact the soil around it really good, then it really doesn't do you any good. Nowadays, we don't use them. We use what's called a diaphragm filter. It's a sand collar, if you will, around the pipe. So if water is leaking along the pipe, it hits that sand. And the key to that is, again, water coming through a dam is not sometimes a big thing. But if it's carrying soil with it, that's when you create problems. So over a long period of time, carrying that soil will end up with a void in your dam, and your dam may collapse. So these collars prevent the soil from leaving. It doesn't prevent the water from leaving, but it prevents the soil, and that's an important aspect of it. As I mentioned, conduits through dam is a weak point. Even if built a new dam, if you don't do it right, that water is going to say, all right, I'm going to just follow that pipe. I'm going to go under it, I'm going to go around it. You see the anti-seep collar, in this case it collapsed, and the dam fell when it filled up the first time. So if you got a dam rehab and you're replacing the pipe, it's got to be done right, because that's what the water is going to be looking for, is a failure of the dam along that conduit. This is an NRCS, their small watershed flood control project. You see what's referred to as the D by 3D. Their riser structures are generally a D width and 3D wide. They're rectangular. They found over the years through research that for their type of application, that shape of riser is the way to go. It's the most efficient. But on some of the smaller ones, this is a dam rehab where you got a new square riser with a trash rack connected to a ductile iron pipe. They can be all shaped. Here's a typical farm pond. You got a corrugated metal pipe with a little corrugated metal with rebars for the trash rack. They work fine for a long time, then eventually they're going to fail. Here's one kind of, you can see the condition of the trash rack, the back, the erosion, the corrosion is already, they actually put a concrete cap around it where they had a leaking joint. But these things are just a ticking time bomb. They will fail. So if you have them, it's just a matter of time. So you need to really, if they're more than 20 years old, you've got to start thinking about replacing them. Talk about outlet protection. So when these pipes flow full, 35, 40 feet per second of water, this is a 30-inch pipe, it can create a small Grand Canyon below the dam if it's not actually protected. And here you see the riprap in that one. So you gotta protect downstream. This is one about the pipe, you see the riprap. You gotta protect it. Because what happens, that erosion starts eating back into the dam itself, creating problems. Sometimes plunge pools, riprap is generally the simplest way to go. Here's a U.S. Rural Reclamation backward basin. The water comes out of the pipe, hits this wall, drops it straight down, and then flows up. What it really does, this is what they look like. When that water is coming out at 40 feet per second, it hits this concrete wall, right here, and all of a sudden that water is forced vertically down. So the energy is taken out of it. So in this case, you don't even see hardly any riprap in the channel because all the energy occurs inside that basin itself. Here's what's called a drop spillway. If your dam's not very high, the best way to dissipate energy is to have that water drop down vertically. Make that velocity go vertically and not horizontally. So here the water would come into this and drop straight down over this head wall into this, what's called an apron, and then flow out of the channel. This is a kind of a combination. This is a drop structure, about 6 foot high, so when the lake is at normal pool, water flows over that and drops straight down. Here's one made out of gabion. Here's a gabion, they're a wire basket filled up with stone. So instead of concrete, this one is just made out of these gabions, but it's the same concept. The water drops vertically down. You can see in the channel itself, there's no riprap because the velocities are very low. We have a drop inlet. I call these bathtub spillways. Here's where the lake is on this side, and the water can flow over 3 sides into the spillway. So you're increasing that L by having water can go into the spillway from 3 different sides. So here's one, so when the lake's full, it can flow over on 3 sides. The problem with this, it's almost like a boat. That spillway is going to want to float. So these concrete structures have a lot of mass to them, prevent them from floating up. So while you increase that L to get spillway capacity, you add a lot of concrete to keep the thing from wanting to float. If your dam gets high, you can't have these drop spillways. You can't have a vertical drop of 50 feet. So now you got to get the water from the top all the way down to the toe of the dam. You generally do that with a chute spillway. Now we're talking big bucks. So now you got not only the weir structure up here, you got all this concrete, and this water is going 35, 40 feet per second. You got to have a nice stilling basin to get that 40 feet per second down to like 7 feet per second when it goes out down the stream. They can be these large dams all over the world have these huge spills. They're passing millions CFS. Here's one that's not flowing, but they're expensive because there's a lot of concrete. You don't see many of these. Sometimes out west, they use these baffle blocks on the chute itself to slow that velocity down. Use some out west because there's a lot of erodible soil out west. So they say, we're going to slow the velocity instead of 40 feet per second going down the chute. We're going to put all these blocks to keep the water from reaching that velocity. They look a little funny, but all this is highly erodible soils, but they use those blocks to slow the water down. Talk about the weirs, because this is where that C factor comes in. We got generally these 6 different types of weirs. What's called a broad crested weir is when it's flat, right across the top of that water. This is the least efficient of all the weirs, but they're easy to construct. You see a lot of them. This is an OG. This is now that C goes from a 2.5 maybe to a 3.5, and you make them their curvature. But you can tell it's a lot more concrete and a lot more finishing, a little more complex, but it costs more to build it. And here's a weir. Instead of being a straight one, they made it curved, so you get the OG, but you also increase the length. So now I'm getting a little more capacity by making it a curved OG weir. Have you ever been out to Hoover Dam? They have these side channels, and here's an OG section. The water flows over here, and then runs down the channel, and at Hoover Dam it goes through a tunnel. Nowadays, you see a lot what's called labyrinth weirs. We want to increase that L. Well, we want to increase the L, but we do not want to make the spillway real wide. So you see the L is lengthened by all this zigzag. Very popular these days. They're concrete, it has a small chute, so the water goes over these and then runs down the chute into the spill. Here's one that's operating during a flood in Georgia. They pass a lot of water. They can be different. What we call each one of those zigzags is called a cycle. So here, each one of these is a cycle. Here's one made out of steel, small one. Instead of concrete, these axle, the zigzags made out of steel plate, not very hard. The one that's got one cycle has a county road on top of the dam, again with the chute. And just lately, the first one in the U.S. is called a piano key weir. It's similar to a labyrinth, but if you look at them in plan view, we call it piano key, looks like that. But it actually is a little more efficient than a labyrinth. So what in this project, it occupies a much smaller footprint. And on an existing dam, to satisfy a lot of the environmental regulations, you want to stay within the footprint of the old structure. You start getting out of that, now you start getting into wetlands and mitigation, and then the cost goes up. So in this case, this is in Peachtree City, Georgia. It used to have a broad crested weir here, and this piano key was just finished about a month ago, and it's the first one in the U.S. You won't see a lot of them. You can imagine the formwork, not a lot of concrete, but a lot of formwork. But in this case, it was a perfect fit for this project. There's actually two others now being built in the U.S. So, again, when your engineer comes to you and says, we got to somehow get a lot more water through your dam, those are kind of the options that he's going to sit down and talk to you. Talk to you about the advantages and disadvantages and the cost. And you can well imagine when we start talking concrete, they're not cheap. Sometimes you just have to have a concrete spillway. Siphon spillways, a lot of times if you have an old corrugated metal pipe, say a 12-inch corrugated metal pipe, sometimes you can just grout those up and abandon them in place, if done right. And then you can replace them with a siphon spillway. The siphon spillway is not, the pipe itself is not at the base of the dam, it's right at the normal pool line. This is one they got, and you have a vent pipe out, they work automatically. And here's one that has 4 cycles. Now right now those aren't acting as cycles. At normal pool, water is just flowing through a pipe like normal. So you see water just dribbling out of the pipe. There's not a flood going on. So here's one where the siphon action is just starting to click in. The lake level went up. So now the pipe is, the inlet of the pipe in the lake is completely submerged. And then when the pipe, when you actually siphon starts, this is what happens. So, and then what happens, that lake will go down and the siphon will start sucking in air and the siphon will stop. So they work automatically. They're great. If they don't handle a whole lot of water, but they're handling small flows on small reservoirs, small watersheds, they're used quite frequently. And you have to have a plunge for them. You imagine this jet of water coming out, it can cause a lot of erosion if you don't. So siphons are good for replacing old small corrugated principal spillways. Open channels, a lot of, back in the day, particularly the Natural Resource Conservation Service, build these flood control dams, and then the emergency spillway would be a vegetative channel off the dam in natural ground. And there's thousands of them built this way. Here's a smaller one. Again, here's a spillway actually engaged with water. Here's one during a major storm. It has 2 emergency spillways on both sides. This is the dam. It's hard to visualize. But you got emergency spillway flowing here and one flowing here. The principal spillway is here, and you see the pipe flow. So you got, the dam looks like an island. And actually, I guess at this point it is. But the problem with vegetative spillways, you see it occurring, they'll eventually erode. And that erosion, in certain cases, will work all the way back to the lake and eventually drain the lake. We learned over the years, mainly with new computers, that we can model the erodibility of these spillways, and we're finding a lot of them will fail during the design stage. So you're seeing a lot of rehab, and we'll show you later today, where these spillways are being abandoned, and concrete spillways are actually being built over the dam itself. But a long time, we went with vegetative spillways, but we're finding they are subject to erosion significantly. Here's one, the spillway is over here, and actually started the dam to collapse. If you have a rock channel spillway, a lot of people say, well, rock's not erodible. Well, at certain velocities and flow rates, rock is erodible. They have joints in it. But if you're lucky enough to have a rock spillway, in this case, you have a training wall to keep the water off the dam, but it keeps, obviously, most rock will not erode nuisance. Gated spillways, real quick, you can have gates that are huge. Sometimes these can be 40 foot high, what's called radial gates. Here's a small one we put in. They have a rubber dam. You see this rubber bladder that hold up this metal gate. And this one works automatically. When the lake goes up, they have a sensor, and then these bladders decrease from here, and it automatically lowers this gate down. When the lake goes back up, the gate goes back. It's a very nice automatic process for this homeowners association. We have here what's called crest gates made out of metal. Here's a gate for a navigation structure. These are called fuse plugs. The whole concept here is when the water gets up real high, these things actually disengage and actually go downstream. You actually got to rebuild them. So you don't see a whole lot of them, but in certain situations, a fuse gate type spillway will work. Here's what's called a fuse plug. This is a concrete spillway. It's hard to see, but on top of it is a erodible earth plug of soil. The whole concept is when water starts flowing over it, it will erode on purpose and act as an emergency release and let a lot more water go out. Those, we model and say, well, all right, this thing will erode in half an hour, and it's all hypothetical, and sometimes they work and sometimes don't. You don't see a lot of them because you're trying to make a judgment on how quick that will erode and let water out. Another big thing is we got a lot of dams, we need to pass a lot of water. You don't own the land on either side of the dam, so you can't put a new auxiliary spillway in. So we're going to put a spillway over the dam. We're going to what's called allow the dam to overtop. To allow it to overtop, we don't want it to erode. So there's a couple ways to do overtopping protection. One is what's called roller compacted concrete, the way Saluda Dam was built. Now it looks like a series of steps. Here's another one. They're generally set so they don't function until at least the 50-year storm. But they're the emergency spillway. This is one in Georgia. There was Gwinnett County. They got here's the dam. It looked like the dam is failing, right? It's over. In fact, people thought it was. It wasn't familiar with the dam itself. Well, when the water exceeded, what happened was this dam had RCC overtopping protection. They covered it up because it was in a park with grass and planted grass over it. So you didn't know this concrete was underneath the soil. But when the flood dissipated, you can see where it washed away some of the soil and kept the dam from failing. So it did its job. Another thing is these articulated concrete blocks can be used for overtopping protection. They're concrete blocks, they're cabled together. Most of these are covered up with soil, so you don't see them anymore. And you can see them here, coming kind of like mattresses, and you kind of just tie them all together. Like I said, most of these are buried also, so you don't see them. So that's the introduction, kind of get you familiar with the terminology, with some of the types of dams that are out there, types of spillways, because you'll see later on in other presentations, we'll mention some of these again in a little more detail. So I'm going to turn it over to John. Is John or you and Jill doing stuff?